Okay, hello everyone. So I'm Taro Hitosugi. So I'm going to talk about autonomous experiments for material science. And then I'm very happy to be here again because 10 or a long time ago I came here once and then I gave lecture. So at that time I was doing STM on oxide surfaces. So you like STM, right? You said. Right, and so many. And then we deposit using pulse laser deposition, thin films. This is a growth chamber, and then it's connected to the low temperature STM. And then, yeah, made the system. And we did many oxides like strontium vanadate. You can see oxygen, and you can see vacancies, or these are titanium d orbitals. And then when I was in Tohoku University, I did this research. And then at that time I came here. But when I moved to Tokyo, I could not bring the STM. So our STM was, I wanted to make the STM the highest resolution in the world with, even though they have a pulse laser deposition. So we made a large foundation. We dig a hole and then poured 400 tons of concrete and then put the STM in the pulse laser deposition. So it's very large concrete block. So I could not bring those 400 tons to Tokyo. So I could finish studying STM.
Did it work?
Sorry?
Did it work? Was it the highest resolution?
Yeah, it is. It is now. The STM is there, and it's still high resolution. Thanks to this large base slab, resonating frequency is very low, and very high resolution is possible. So in Tokyo, I started a new thing. That is today's talk, automatic research. At that time, the STM, the operation of STM was automatic. The scanning is automatic. And then also we did remote. So I thought we can utilize machine learning technique and then make the system autonomous. So that's today's talk. And then before going that, I'll little bit show my research. I found these electron titanium dioxide. I think you deposit this titanium dioxide. Also, I work on the approach to the science is very similar to you. I try to make the problem simple as possible in the model, make a model system. So recently tackled the solid state battery research, and then the problem is that the oxides, positive electrode, and solid electrolyte, this interface is the key. Always electrochemistry happens at positive electrode, solid electrolyte interface. So we wanted to understand the interface. And then this is always a problem of the solid state battery. So we make model interfaces using epitaxial thin films, and then deposit solid electrolyte without taking out the air. So we make a perfect interface and then study the interface. So the approach done in here is very similar. The catalytic, if you want to understand catalytic activities, create the model sample, and then see the intrinsic properties. So we deposit thin films, epitaxial thin films, and understand these interfaces. So one result is that we want to have a high ionic conductivity across this interface so that we can charge battery instantly. But the researcher in electrochemistry does not know whether this interface can be very fast ionic conductivity. So we made a model and then proved that, this is our system. Please come to our lab. This is a manual system. Many chambers are connected. Thin films growth, and also prober, XPS, and then we can understand the interfaces. This is a picture, and then we can prove that this is not today's topic today. So I will not go into the detail, but anyway, we show the interface, solid state, solid interface, the ionic conductivity across the interface can be very high. So that is very good for solid state battery research. These values, the interface resistance, can be lower than the ionic lithium-ion battery, the liquid system. So solid-solid interface can be better than liquid solid system. So this is very good sign for solid-state battery. So these are the research, and then we want to accelerate this research. So that is a topic. That's why I started this autonomous experiments. And then I think you use machine learning and robots in daily life. And in Japan, many robots. So this, you know, this, if you go to restaurant, this serves here. Is it common here? No? I saw the robot cleaning.
Yeah, that's new. That's like a week here.
That's, how about this? This is a hotel's frontman. This is now the robot is doing. So this is dinosaur would talk to you and then you can check in. So the robot itself is expanding, and then also the cars. It's like a robot. I always use those automatic driving because it's like a sensors sensing all the direction and then protecting us. So I always use those autonomous driving. So robot is expanding, and then of course these directions, including AI, is really becoming the workforce for the science. So the last 2 years ago, the Nobel Prize, physics and chemistry, both these prizes are related to machine learning. And then nowadays we have to think that machine learning is really driving our science. So there's no doubt that we do not use, there's no doubt that we should use AI, also the AI controlled robots in the science to accelerate. And at this moment, the advancement of robots, advancement of AIs are very fast. And then how the research itself is changing, that is unknown. That the reform of science itself is a new challenge. And then a human and robots or AI, how we collaborate, that, and then create a new research environment. That is really a challenge and ongoing. So we are really at the age of changing. That's my understanding right now. And then let's look for the material science. And then, yeah, number of materials, so large. Materials parameter, we want to tune many things, oxygen, partial pressure, temperature, composition, many other parameters. And then our material search space is so large. So how we explore this material search space, that is the problem. And then this autonomous experiment is one of the key to explore the materials space. And this revolution really accelerated in 2020. So this is a UK Liverpool group. So in 2020, they demonstrated that this is a robot. And this robot move around this lab and do research night and day, 24 hours. And then what's surprising is that this robot do 688 experiments in 8 days. Very large number. No human can do experiments like this. So we have to think that there's a change in how we do research. And then this is beyond automatic. This is autonomous. There's a large difference between automatic and autonomous. So automatic, we program humans program. But this autonomous means that the computer decide what to do next. We use Bayesian optimization. And then experiment is done by robot. And that data goes back to the computer and computer decide what to do next. So there's no human intervention, all done by autonomous. So we should think that this autonomous technology would change how we do research. And also in 2020, we demonstrated autonomous experiment. And then this is how it goes. This is a vacuum chamber, and then we do a thin films growth. And we just ask the system to maximize the lithium ion conductivity or any maximize the XRD peak or anything. And then this is only the representation for one-dimensional optimization. And then white line is if you do all the experiments, you'll get the peak at like around 300 degrees centigrade. The system guess the best temperature. And then research synthesis is done all by robot, and the sample is transferred to the measurement chamber, and the ionic conductivity measured, and then go back to this Bayesian optimization, and again prediction is done, and next conditions predicted, and growth by the automatic chamber, and measurements. This goes cycles many times, and then without human intervention. So if we come to the school again in the morning, then already this material is synthesized, and all these data is collected, including the process parameters, temperatures, everything is collected in digital way. So using that data, we can do materials informatics. And then there's many research going on. So I don't know if this video works. The internet is a little bit slow, so let's skip. Oh, these are robots doing experiments. Or I hope this works. This is a catalyst fabrication OER from a Korean group. And then the robots are doing many experiments. So that we use this hand-like type, and then also this transfer robot. We use several types of robots, a few types of robots. So these can now help doing research. And then the important thing is that we ask this repetitive work to the robots, and the human do more creative, more fun part. So that's the direction. So the direction of this research can be divided into two. So first I talked about the autonomous experiments. This is called closed loop. The prediction is done, material synthesis is done, and then measurement is done. So this is cycles very fast. And then if we decide what to fabricate or what parameter to maximize, then this really works very fast. But the other loop, the bigger loop, so this is like what to do, decides the hypothesis or generate hypothesis or decide what to do. So this is a cycle, large cycle, and this is very important. And now we have a whole bunch of data coming out from this closed loop, and then a calculation and prediction, and then a generate hypothesis. So using like an AI agent or LLM, they also start using that to generate hypothesis. And then not only that, of course, researchers, ideas, craftsmanship, that's important. Of course, this is a very important part, and then you also incorporate in this cycle, and then do experiments. So these both loops are very important. And then I strongly think that the next generation theorists are going to involve in this curve cycle. So now I ask many theorists to use our autonomous system. So theorists can predict, but you have to persuade researchers or experimentalists to test your hypothesis. That takes time. Sometimes experiments doesn't do experiments that you predict. So if you use autonomous system, you can test your hypothesis. So in the near future, the theorists can really test their hypothesis by yourself. Please, you want to try? Yeah, I try to invite many researchers, but so far, theorists are always a little bit hesitate because they always say that oh, I'm not good at experiments. I will break your system. But I always say it's autonomous. You cannot break the system. So please use our system. You can log in from Vienna to Tokyo, and then you can really operate remotely. So that is the next research style. So today's talk is that how can we accelerate our research, and then the direction of autonomous research, and then autonomous system in our lab. I'll talk about a little bit in detail. And then I want to start from why I started this direction and how can we accelerate our research. So let me start from my personal experience. I want to talk about why I focus on this research. And then I want to start from my failure or mistake I had when I was in Sony. When I was in Sony, I was doing marketing and sales. So I went to many places and then press conferences, and then so this is a new product, Sony's product. And then I was doing product planning, also marketing and sales. And at that time, I was working on this device called Clear. So this can listen to music, take photos, edit Word, send emails, and make a phone call. It's like a nowadays smartphone. But the important thing is that our device, same concept as smartphones. We did 5 years earlier than iPhone came out. So we are really ahead in this smartphone. But however, we cannot make a smartphone revolution. Nowadays, many people use iPhone, and then even I use iPhone now. And then this is discontinued. So this disappeared. So I always think that I always use iPhone, and then I think that why we lost this competition, and then why we could not make the revolution. And that is related to this autonomous research. So because of time limitation, I only talk 2 reasons why I think we lost this competition. The first one is that we had self-constraints. We limit by ourselves. So what we think was that this Sony, we are Sony, so there's many artists, Sony Music artists. So we thought we have to protect musicians. So we thought that the copyright is very important. And then we limit limit the usage of this, you cannot copy this music or distribute to anyone, or we have to anyway protect copyright. That gave a additional user interface, bad this deteriorate the interface, user interface. And then also we had a business called Walkman. Walkman is a small device you can listen to music. So we have to think about what is the difference between the business between Walkman and then this Courier. So that thing we are limited or constrained. And then what the Apple's did was that they don't have any musician in the Apple, so they don't have to think about copyright. So their software, they can freely copy or send music. So the user experience is much more friendly and easier. And not only that, those are some self-limitation. Our limitation made this less user experience. And I always think that this self-constraint is not good. And then I always talk to students that don't limit yourself, think freely. And then that would open up your next step. So let's think about our lab. Do we have self-constraints in our lab? Yes, we do. So if we see many students researching in our lab, I ask students, is that experiment does human have to do it? It can be done by robots. It's repetitive work, it's simple work. Why you do it? Why human do it? I ask to the students. Student says like this, oh, I taught from other students, so I have to do it like this. So already there's a self-constraint. So I always tell students, think freely and let's ask the robot to do it, and then you do more creative work. So there's many constraints that the human have to do. Many people think human have to do the research. So we have to be free from that. So that's one thing we have to think about. And the other is that the systemization. So I said, our system can take photos, listen to music, send emails, call, make a phone call. All those are in the device, but it's isolated. It's not systemized. So what I learned from Apple is that they also use internet and then made a system, total system, and then a very user-friendly and a total system. So I learned that the isolated or standalone is not good. Make all the things systemized, and that gives value. So if I think about our lab, all these devices are standalone, and then the human have to connect. So it's like a courier. It's a standalone. So the next generation lab, I can easily imagine. So these are disconnected and standalone. So it should be systemized in the next step. So we can easily imagine the next lab, systemized lab. And then we can follow the term, this case. This a little bit ago, many people talk about what car industry would change. Connected, autonomous, shared, and electric. And then, yeah, this really applies to our lab. So everything is connected. So the computers are connected to each devices and understand what is happening, what has to be done next. All those things are controlled by the computers connected. And then autonomous. Yeah, all the system is autonomous. And then of course, sample transfer is automatic, and that the system itself is become autonomous. So that direction is what I'm going to talk. And then additionally, the important thing is share. So implementing the integrate a researcher's knowledge, experience, and intuition into the system, and then we can share this to everyone. And then of course utilizing the data too. So this is the direction we can see for the future. And indeed, there's a number of experiments, like autonomous experience papers are really increasing since 2020. And then nowadays, the largest advancement in this years is that AI agents now. So ChatGPT and Gemini, if we ask something, they seek the web page and then report us. And now our system or simulation can be controlled by this ChatGPT, Gemini. And then the AI would instruct our system and then do the experiment and then report. So this is really happening right now. This is a really cutting edge state. So doing the research labs automatic and autonomous means that this AI can use the lab. So this is a large change. What is going? So it's like making the instruments AI ready. So this is the direction. And also the data is going to collect it and then share. So that means from each labs or shared facility, data is stored in a cloud, and then these data are shared. And then make it to knowledge foundation. And then this is not limited to one discipline. So many disciplines, including life science, agriculture, earth science, they are united. And then that is the overall direction. And then I have to say that so far, we have to apply these techniques to optimization. This is very important, right? We have to choose the right topic. The optimization. This is the most strongest part. If it's repetitive work and then the reproducible experiments, then this fits. These automations fits in an optimization. And then, of course, as a scientist, we have to go to find new classes of materials or completely new, like a serendipity. That is still technique is developing. So we are now focusing in this stage now. And then many techniques are coming out to really go to the something unexpected. That is a current situation. So if we start doing the autonomous automation, start choosing the topic from optimization, I think this is the important part. If you start from this one, sometimes it's not efficient or useful. So at this stage, this optimization, and then this is the latest topic now. And then I'll talk about a few examples. This is a two-dimensional optimization, like partial pressure and annealing. These are done autonomously. And then in this two-dimensional parameter, this automatically finds out this area have a higher conductivity. So this is like optimization. And then it can be done like 3 dimensions, 4 dimensions. If it's human, it's very difficult to optimize 3 dimensional or 4 dimensional. But this is a mathematical science. So it can, Bayesian optimization can optimize these parameters. Also, this is an example of finding new ionic conductors. So we deposit 2 types of materials. It's a sputtering and change the sputtering power so that can change the composition. And then measure the AC impedance measurement and Bayesian optimization. So this closed loop. And I also, so this is again, it's like making a phase diagram. The automatically making a phase diagram. And the result is like this. And then we see a 3 region, and then blue part is low ionic conductivity, so we are not interested in. And then red part is high ionic high conductivity part. And then this region 1, starting region 2, this is looks like ionic conductor. And then actually it is ionic conductor. We find a new ionic conductor, but it's not the world's best. So we are now looking for the world's best one. And then as a scientist, what was interesting for this research is that we find something unexpected because we are measuring many parameters, measurements. We find something unexpected. And in this region, it looks like electrons are also moving. So it's like electron and ion conductor. So this is electrode materials. Actually, we confirm that this works as an electrode materials. We try to find a lithium phosphate, try to find an electrolyte, but end up finding electrodes. So something unexpected can be found using these techniques. So going further, we now characterize many properties. So we want the complete data. If you want to do good machine learning, we need dispersed data. So we want to collect all the data. That is the very important part. But it's time consuming, and if humans do research, that's not possible. So we ask the robots to do all the data collection. So that's the next step. So now we synthesize, and then we bring into many kinds of instruments. These are the gel scanning electron microscope, and this is the X-ray diffraction, and then this is UV vis. So this is a total system. So you came to see all that. And here we have a sputtering system. In here, we deposit a film, and then we have a metal mask. You can change the metal mask. And then you deposit electrode materials with different chamber. So we can make a device inside here. And then make the electroconductivity measurements. And also this is directly connected to the scanning electron microscope. The sample goes into the SEM, and then the automatic focus, and then the EDS. All those are done automatically. And then take out to air. We have Raman spectroscopy, and then go to X-ray diffraction. So this is one example of X-ray diffraction. So we use these robots, and then all these are the experiments for us. Then the teaching the robots is very easy. If you want to move these things to here, then we just grab this arm, the robot's arm, and then like this, and then all the motion is taught to the robot. And also we have to like a 1 millimeter adjustment, and then we use those game controller to control the robot. So it's like playing a game. So chemistry students or our lab's chemistry students can teach the robot now. So we don't need any programming for teaching the robots. So like this, we utilize this 1 centimeter, and the robot would really nicely grab and then bring it into the X-ray diffractometer. And then these are really done overnight, and then how we do research has changed. Like one student's workflow was like this. First day they make synthesized materials. Second day they characterize. Nowadays, the student's workflow is like this. Overnight, the robots synthesize the materials, and then in the morning, all the sample is ready. So they do measurement that only human have to do. And then when he or she go back, then put the sample holder into the system, and then overnight, the system make a sample. So how we do research, the workflow of a student is changing. And then we utilize all these systems, and then one important thing is that these are modularized. This is important part. This system is custom made, so it's very expensive, but this is not the direction we are going, everybody is going. Try to make the system module as possible, and then you can buy each module and then bring into lab and just connect it. And then all autonomous. And then we need flexibility. Research always change. We need flexibility in research. So that flexibility is very important for research. So modularization is the point. And then already like a robot and X-ray diffraction, that is a set already start selling. Also these gel, this automatic transference system, and then this SEM is beginning to solve. So in the future, it's going to be a plug and play manner, and then that means cost is reduced, and then everyone can use these systems. And the materials, and the cyberspace is changing. So one of the problem is that the data format is different. Like X-ray diffraction, SEM, always it depends on the vendors, the format. So it's really difficult to collect data. And now we ask all the vendors to standardize. We asked many standardization. So like if we want to connect these devices, sample holder is standardized. A sample itself is standardized. So standardization is the key to connect all the things. So now we ask this MIME or MAMO. This is XML format. And then all these, including processes, X-ray diffraction, SEM, all of them are in a single format. And then collected into the data lake. So it's very easy to collect all the data into one database. And already we demonstrated that on the data lake, on the cloud, we analyze the data. And then from that, we get the Bayesian optimization, data for Bayesian optimization. And then prediction is done on the cloud. And then only the results, only the next deposition condition is coming from the cloud. And then utilize as an autonomous experiments. So all the things are modularized. In the internet, we call this microservices. And then this is a really modularization, even for this software is starting. And then we already demonstrated that we have X-ray diffraction pattern. So we know where the peak appears. And then we demonstrated for lithium cobalt oxide, intensify the 003 peak. And actually, the robotic system, autonomous system will intensify this 003 peak and then tune the temperature. So I asked the theorists to send the structure file, just then we can convert to the X-ray diffraction pattern. And then the composition, like ABO or O3 or, and then the system would autonomously fabricate your sample and then measure the properties. So that became possible. And then, okay, less than 5 minutes, finish up. So our direction right now is that we go beyond human. So far, it's just a replace of human. That's not the goal. So this blue curve is what humans can do. And this red curve, red circle is what robots can do. We find this overlap point And then nowadays, humans' work is replaced to the robot. So this part. But this is not our aim. We want to do experiments that human can never do. So that's our direction. So one example is this surgical system. So if it's human surgery, then we have to open up our stomach and then see the inside. But if we use robot, the human has only 2 hands, but robots have multiple hands. And then we just make a small hole and then stick these rods into our body, and these have camera. So less burden on patients, small wound. This human can never do. Also more detailed work, like humans' finger always vibrates, cannot do very fine work, but robots' finger doesn't vibrate. They can do more precise surgery. So this human can never do. So we can design our experiments really completely differently if we think that the human do not do experiment. Only the robots do the experiments. So one example of this is what we are doing is a mixing of samples. So like a mortar and pestle, we always use this mortar and pestle for the experiments mixing, but that strongly depends on students. And then why this depends is that it's not quantified or quantified. So if it's robot is doing this, then we can ask this to do like a 10 Newton, and the next experiment 12 Newton, 15 Newton. So it can be quantified. So also there's a sensor here, and then we can measure the vibration or the frequency dependence, or we now have a glass mortar and pestle, and then we can do optical measurement during grinding, or we can shine X-ray or UV for the enhancing the chemistry. So we can really go beyond human, and then higher reproducibility, and then really go for new chemistry. So that's what we are working on. More that would expand the more parameter space and then find a new chemistry. We recently started doing this MOF, and then we can make a different polymorphs using these system. So end up with 2 more slides, and then one is that empowering researchers. That is very important. Do I think I'm happy using this system? If I'm asked like that, it really encourages me or excites me. It's like when I got the driver's license. When I was 18 years old, I got a driver's license. I thought that with car, it's a tool. Then I can go to the many places and then see the sightseeing or eat good food, and then it expands my area. And now same thing is for the experiment. Just before us, there's so large material search space, and now we have AI and robots. So it's like a tool, and we can explore this large space, and then we can find new materials or new applications. So I'm very encouraged, and then I feel excited about this direction. So this is the summary slide, and then development of autonomous research labs. We are going modular and standardized, and then we use 1 centimeter by 1 centimeter, and then this can also adapt 1 centimeter 5 samples. So this module, if you standardize to the 1 centimeter by 1 centimeter, then you can immediately use these systems. And then we need to spread this technology, and then we have to reduce the cost, and then we have to do sharing the system. And we interested in something unexpected. Something unexpected always start from observation. We have to find something different. So we need observational measurements. So multifaceted or multimodal measurement is the key. That's why I make many measurement module and then connect to see something unexpected. And now we are focusing not only thin films, we are focusing on solid materials. And that is really challenge. Solid materials is always challenge because it has shape or it changes the shape. So more robotic technology is needed. AI-driven robotic technology is needed. So this is a frontier for robotics. So we need the frontier of robotics to deal with material science. So we can collaborate with those robot researchers. We are collaborating. So with that, we are trying to create new chemistry and materials. And this is the team. So we have many new type of researchers, not only chemistry, but they know AI or machine learning and robotics. And this is a new type, these are a new type of researchers. And then I want to encourage many researchers that can utilize AI and robots to accelerate material science. Okay, with that, thanks for the funding agencies, and then thanks for your kind attention.